Welcome back, everybody. In this video, we want to prove that if you have a bounded function with a finite number of discontinuities, then that function is still integrable. Right? We already knew if you were a continuous function, you were integrable. Now we want to be able to insert at least, 17 discontinuities and not worry that we're going to lose integrability. Now, in order to prove this, we are going to use sort of an auxiliary result first. So we're going to start with that. So this theorem I'm going to call integrability at an endpoint. And the idea here is that if I know that I'm integrable, except maybe I have this discontinuity at an endpoint, right? Like that kind of worries me a little bit. As long as my function is bounded, I actually will be integrable over the entire interval. So start with my usual setup. I have a bounded function on a closed interval, AB. Call it f. And I'm going to assume, so if for every value between a and b, we have f is integrable on, well, let's do the closed interval from c to b. Okay, so if I draw a little picture on the right, okay, I have maybe my a and my b on the ends, and I choose a c, and I can make that c pretty close to a. Okay, and I can check, is my function integrable on CB? If it isn't, okay, I got a problem, right? F should be integrable on any subinterval. But if it is, hey, that's pretty good. And what if it is for every possible C, except, maybe if C is equal to A, right? Well, of course, if C is equal to B, there's nothing really to check. But if C is equal to A, maybe I don't know. But if I know it for everything between A and B, then I actually know, this is the conclusion, then F is integrable on the closed interval AB. Okay, now of course there's a little, why did we choose CB instead of maybe not knowing about what happens at B, right? So maybe it could have been everywhere from A to C, right? So maybe we put the C over here and you know it all the way from A up to C. And of course, a similar proof to the one we write down here will work in that situation as well. And of course, we do want that. All right, so we're going to prove this, and then we'll show why this is really enough to conclude that having a finite number of discontinuities will preserve integrability. So let's get in here. So if I want to show that f is integrable, then I can use the integrability criterion, and that's going to require me to show that there's some partition such that the difference in the upper and lower sums is bounded by some positive multiple of epsilon. So hey, I need to start by choosing an epsilon. So let's let epsilon be positive. And what I'm going to do, because I know that I have all this cool integrability junk, at least when I'm away from A a little bit, I'm going to choose some C, which is to the right of A, but not too far to the right. Okay, in fact, it's going to be within, like, let's say I put epsilon over here, so this would be A plus epsilon. I'm going to choose some C in between A and A plus epsilon. So we'll let C be in the interval A to A plus epsilon. All right. Now, I know that since C is not equal to A, then F is integrable on the interval CB. And so I can find some partition such that the upper and lower sum of F on that interval, right, there's a partition of CB, on that interval I can get that to be less than some multiple of epsilon. Okay, so since F is integrable on the interval CB, there exists a partition, and I'm going to call it X, but I'll put a little C up here since it does depend on this C I've chosen. So this is a partition of CB, such that if I compute the upper sum minus the lower sum, I get a value less than K epsilon for some positive constant k, right? Does not depend on epsilon. Okay, now I can use this partition of CB to get a partition for the entire interval AB by simply including the point A at the beginning. Okay, so I can define a new partition. Let's just call it X. This is a partition from A to B by, well, the first thing will, of course, be A. The next will be the beginning of the XC I had here, so that'll be a C. And then I have, well, all the rest of the stuff. And I don't really want to label it. I just know it'll end at B, and this here is my XC. Okay, so I just include one extra point at the very beginning, and that gives me a new partition. Okay, and of course it's a little bit bigger. All right, now, what did we know about f? Yes, f was a bounded function. So that means, so since f is bounded, there exists some positive number m such that the absolute value of f of x is less than m or equal, that's fine, for all x in our interval AB. All right, so let's try now to compute the difference in the upper and lower sums of f, not on xc, but on x itself. So we have the upper sum minus the lower sum is equal to, all right, so first, the way I would compute this is by looking at each of the intervals. So the first interval is from A to C. So how would I actually compute this? I would look at the supremum of f applied to this interval AC. Of course, I would multiply then by the length of the interval. But let me save that to the end because I'm also going to have to subtract the lower sum, which means I'll have to subtract the infimum of f on this first interval. Okay, and each of those will get multiplied by the length of the interval AC. Okay, so that's the first bit. Now I need to compute all the rest. But all of the rest are precisely the upper sum minus the lower sum for XC. So all the stuff that came from this partition. So this is plus UFXC minus LFXC. Okay, so what do I know? This supremum, what is the biggest it could possibly be? Right, oh, because we knew f was a bounded function, this thing is less than or equal to m. Okay, what about this infimum? Well, since we know the absolute value of f of x is less than or equal to m, the smallest the infimum could be is negative m. So the biggest this difference can be would be m minus negative m, and hence this bit here is less than or equal to 2 times m. Okay, now the length of AC, well, we know that C lies between A and A plus epsilon. So this length here is less than epsilon. And then, of course, well, we were able to assume up above that the difference here of these upper and lower sums is less than K epsilon. And so in total, we know that the difference of our upper and lower sums is less than, well, let's see here, 2m plus k times epsilon. And 2m plus k is certainly a positive number. So by our integrability criterion, f is integrable on AB. There we go. Okay, so we finished that proof, and now I claim this is enough to get our big result. So big theorem here. Bounded functions with a finite number of discontinuities are integrable. Okay, so our setup is as usual. F goes AB to R, F is bounded. Okay, and now, well, the rest of it is basically what the name of the theorem is. If F has a finite number of discontinuities, then F is integrable. So let's draw a picture to really show what's going to happen here. So I have my function, and there's A, and there's B, and I have some finite number of discontinuities, okay? And it doesn't really matter if they occur at A or in the inside, but we'll put one over them at A, and maybe there's another one here, and there's one here, and another one here. All right, and I'll call this, I don't know, C1, C2, C3. All right, so in our previous video, integration across an interval, we showed that if we are integrable on subintervals, then we'd be integrable on an entire interval, right? Namely, we break it up at some places, right? So if we went from A to C and then from C to B, we knew we were integrable on each of those subintervals, then we are integrable across all of AB. All right, so if I can show that I am integrable on A to C1, C1 to C2, C2 to C3, C3 to B, that would be enough. Or if I want to break it up in other ways, like that's fine too. In fact, here's what I would like to do. I want to break this interval up in a way that I only get one discontinuity in each interval. Furthermore, I would like to make it so that the discontinuities always show up on an endpoint of each interval. Okay, so for example, I can toss, I don't know, some little point there, and then I'll break it up at C1. And then I'll toss another point in the middle here, and then I'll break it up at C2, some point in the middle here, break it up at C3, and now we're good. Okay, so we've got these things broken up. And so now here's the idea. Let's look at the first interval here, right? We'll call this I1. We know that F is continuous on I1 except at A. All right, but that means that if C is in I1 but not equal to A, then and maybe we'll need a little point here. I'll call it D1. Then F is integrable on the interval from, say, C to D1. Okay, so I stick a little C in there. And I know that my F is integrable everywhere from C to D1. It doesn't matter which C I choose as long as it's not equal to A itself. Okay, but by the previous theorem, if we know that we are integrable on an interval except possibly at the left endpoint or the right endpoint, then we know that it's actually integrable even at the left endpoint or the right endpoint. So I would conclude that F is integrable on the entire interval I1. And now I can do the same thing on the second interval. Maybe we called it I2. And I say, well, okay, the only discontinuity I have is on an endpoint, that's C1. Therefore, by the exact same argument, I'm integrable on I2. And I keep going, right? Here's an I3. Again, only the one discontinuity, and it occurs on an endpoint. So this was the whole purpose of me breaking things up so that I had exactly one discontinuity, and it was always on an endpoint. Okay, so this is the idea of the theorem. Now to make this precise, we're going to make a proof by induction. All right, so obviously if we have a finite number of discontinuities and that finite number is 0, then F is continuous. Okay, so if f has 0 discontinuities, then f is continuous, and we already know that a continuous function is integrable. All right, so that's kind of an easy base case. So what if f has 1 discontinuity? If f has 1 discontinuity, well, there's actually some cases. Okay, so then let's call it C or C1. How about that? Then, well, okay, case 1. If C1 equals A, so if it's on the left endpoint, or C1 equals B, so it's on the right endpoint, then, well, we know f is continuous on, well, let's see, every interval of the form. Okay, so let's break this up here. I'll use black here for if I made C1 equal to A, and I'll use red if C1 was equal to B. So if C1 was equal to A, then I'd be continuous on every interval of the form, let me call it D comma B. For D, something not in AB. Oh, we said we're going to do that in black, didn't I? Okay, let's try to make that black. So every interval of the form D comma B for D in AB. Okay, so as long as my discontinuity is removed, okay, then I continuous the rest of the way. Respectively, okay, now if the discontinuity is on the other end, anything of the form AD, AD for D in AB. Okay, and by the previous result, I then know f is integrable. So by the previous theorem, f is integrable on the entire interval AB. Because if I'm continuous on these intervals, of course, either way, this implies f is integrable on those intervals. And so if I get everything except for the endpoint, then I win. Okay, so then there's the third point, right? What if, or the third case, what if C1 is in the middle? So if A is strictly less than C1 is less than B, then I'm going to break this up. Okay, so I'm basically using that picture we had up above. Okay, but now we don't have as many points to worry about. So I have A, B, and I have C1 somewhere in the middle. And so what I will do, okay, let's see, we've got our discontinuity. That'll be in green at C1. And I'm just going to break this up. And in fact, I can just break it up at C1. All right. So if I break it up at C1, now I have these two intervals, A to C1 and C1 to B. And so by what we just showed, right, so by the previous argument, f is integrable on A C1 and on C1b. Because there's only one discontinuity and it's on an endpoint, either the right or the left. Okay, but we proved in the previous video, integration across a divided interval, that if you're integrable on both of these subintervals, then you're integrable on the entire interval. So you are integrable on AB. Okay, so that handles the case where we have one discontinuity. Okay, fine. If f has n, let's say greater than 1 discontinuities, C1 through Cn, then what can we do? Well, here's where we're going to use induction, okay? We're going to assume that We know that the result is true for any number of discontinuities less than n. And we're going to then show that the result holds for n. All right? So maybe it'll help to draw a picture here. So let's see. I have my AB. Now, I don't know if the C1 through Cn lie on the endpoints or in the middle. I'm going to draw it as if I have one in the middle, but I don't think that should matter here, right? Let's see. So C2, dot, dot, dot. Okay, we have a Cn. All right, so I have these n discontinuities somewhere in here. Now, what I'm going to do is divide up the interval, and I'm going to divide it. I'm going to go to the leftmost discontinuity, which could be at A, right? We know that. And then I'm going to find the next, I said rightmost, leftmost discontinuity, and I go to the next leftmost discontinuity, in this case C2. Okay, so I have C1, C2, and I'm going to divide somewhere between C1 and C2. Okay, so we call that, I don't know, D. And now I know that the interval D to B has n minus 1 discontinuities. I also know that the interval A to D has 1 discontinuity, and 1 is certainly less than n as well. And so by induction, I know that f is integrable on both A to D and D to B, and hence on the entire interval A to B. All right, so let's write that down. So choose, and of course we could do this, right? I wrote these C1 through Cn in a way that they're ordered, so let's actually order them here. So C1 is strictly less than C2, etc. So choose a D between C1 and C2. All right, well now the interval A to D contains 1 discontinuity. Oh, I feel bad, I wrote it as ONE before. 1 discontinuity. And we already handled the 1 case. Okay, so it contains 1 discontinuity, which implies f is integrable on AD. Okay, the interval DB contains, well, it's got all of the discontinuities except for C1. So it contains n minus 1 discontinuities. So by induction on n, f is integrable on dB as well. But now we know we're integrable on AD and on dB, and so this implies f is integrable on the entire interval AB. Okay, and that completes the proof. All right, so we had proved that continuity implies integrability, but now we know if you have a finite number, and finite could be very big, right? You could have 17 trillion discontinuities, you're still going to be integrable. All right, so the next goal is to figure out what happens if we drop this restriction on finite. What if we have an infinite number of discontinuities? All right, the best is yet to come. We'll see you next time.